Hello everyone and welcome to NSBA's Night School, Introduction to Steel Bridge Design. Today is June 20th, 2016, and this is Session 3, Steel Material Properties, presented by Carl Frank. My name is Christina Harbour and I am with AISC's Continuing Education Group. I'll be moderating today's presentation. I want to introduce today's speaker. Dr. Carl Frank is the Chief Engineer at Hirschfield Industries. Prior to joining Hirschfield, he was a member of the Structural Engineering faculty at the University of Texas at Austin. His research work has included the fatigue and fracture behavior of welded and bolted connections, fatigue behavior of cable stays, strength of composite girders, and fracture behavior of twin box girder structures. He has participated in the virtual assembly effort underway at Hirschfield, and as well as the implementation of new welding and inspection technology. Welcome, Carl, and I'll let you take it from here.
Okay, thank you, and good evening. I'll be talking today about a little bit of metallurgy. We're going to be talking about hot rolled steel and some unique requirements for bridges and something we call high performance steel. And I just want to point out that the reason most of you maybe have had some design experience in steel, and the reason why we're doing something that's dealing with steels for bridges is there are special requirements for the bridge steel that are different than what's normally used in buildings. And so we're going to highlight those and some of the reasons behind those. And then we'll talk about also some changes in the bolting material specifications and anchor rods. How do I switch slides? It's not moving.
Are you in the full screen mode?
Yeah.
Okay, at the bottom left?
You should. Okay.
Yes.
Okay. Okay, so I apologize. I'm getting used to the controls here. But if we look at historically how steel was made over the last 200 years or so, it started off with processes that made small amounts of steel, and then we developed in the mid 40s, 1940, we were doing it all with open hearth. Then we had the basic oxygen furnace come into play. But now you see trending is the electric furnace steel, and this is the steel that used to be called mini mill steels because these were small mills that made it basically from scrap, and so they didn't use iron ore as a major ingredient. They used mainly scrap, and that's true nowadays. Although there is some ore added, most of the steel that's being made is from primarily from scrap. So this is one of the reasons that steel is one of the most recycled materials. Is basically whatever is available out there in terms of scrap steel is remelted into new steel. And it's done in an electric arc furnace. And these are smaller furnaces than the conventional integrated mills. But basically, they can melt a heat of steel in 35 minutes. And it uses electrodes, carbon arc electrodes, which are used to melt the steel. The scrap is actually segregated, and they have different qualities of scrap. And that determines really the chemistry of the steel. It's a very efficient process. They can very quickly melt the steel, and after they melt it, the steel comes out of the bottom of the furnace, goes into a ladle, which goes over to the another site where the steel is modified in terms of its chemistry. And this is done to refine the chemistry and to ensure that they get the quality of steel that they have. So it's this, after this process is done, the steel chemistry is sampled at this point. This is where the final steel chemistry is done. And it goes from here to a process that's rather new to the U.S. steel industry. The old way to do it is after you made the steel, you would pour it into an ingot, and that ingot would be a big chunk of steel, which would then go through a roughing mill and be reduced in size. But now all of the steel is made with continuous casting. So we take this metal from this, and this is the ladle that we just looked at. It had the chemistry adjusted and the final steel. And at the bottom of the ladle is this liquid steel comes out, and this is shown schematically coming down here. It goes into something called the tundish, which is just a bath here to contain that steel. And then it exits the tundish down into this mold. And this is the neat stuff because this is liquid steel at the top, and as it drops down here, it's cooled by water spray, and it solidifies from the outside, and when it gets all the way down to the bottom, we have solid steel. So this is a continuous casting process. And for example, if we're making wide flange shapes, they end up coming out looking like this, and they're called near net shapes. They look like almost an old I shape, very thick webs and thick flanges, which are then subsequently rolled to the final shape. If it's plated, it's going to come out in a slab. But this is the way most of the steel is made, and in fact, almost all the steel in the U.S. now is with a continuous casting. So we have, at the end, we have a slab of steel, which then we must go through and roll down to its final side. And the steel that we're talking about is called hot rolled steel because it's rolled at a very elevated temperature. And the reason for doing that at an elevated temperature, we're in the austenite phase of the steel, and it's rolled at this high temperature. And the reason for doing it is that when the steel is in this phase, it's soft and it's ductile, which means it's easy to roll. And there'll be rollers at the top and bottom, and these create these elongated grains, and then later on, as it cools down, we get these finer grain structures. And this can be done in one stand like this and reverse rolled, or it can be done in a series of rolling stands where as the steel passes through each set of rolls, it's reduced in thickness. And in this case, it would be a continuous rolling process. Now, we have to talk a little bit about what's happening internally in the steel as we're cooling it down. The steel starts up here at this very high temperature, and we're showing here temperature versus percent carbon. And this is what is called a phase diagram. And this is just for the elements of iron and carbon. And we start out at a temperature way up here, and as we roll the steel, we're going to be rolling it in this solid phase here that's called the gamma phase, and then we're going to cool it back down, and then into this range is where we're going to be using it. What's unusual about this phase diagram, sometimes you've heard of phase diagrams where you're just talking about liquid and solid phases. Well, these are different solid phases that occur at different temperatures and make the properties of steel rather unique. There's something that happens at this chemistry, if you're at this weight, that it goes completely from a liquid into a solid right in one temperature range. And this is called a eutectic point. Down here we have something that looks like that, but it's a solid phase going into two solid phases, and this is called a eutectoid. And this will become more important to us. To give you an idea of what a eutectic point is, if you've ever soldered an electrical connection with 60-40 tin solder, if you notice when you're soldering, it's a liquid, and then when it cools, it just immediately turns to a solid. And that means it's going right from here down to here. And that's what would happen with the steel out here. But this is way too high of carbon. We're typically over in this range here where I've shown this green arrow, green line. This is the typical chemistry of a structural steel, talking about carbide carbon contents of around 0.2. And this is typically where we are. And so we're going to be starting out here. We're rolling it in the austenite range. When we get down into this range, the actual molecular structure of the steel will start to change. Here it's a face-centered cubic structure. We start forming in here the alpha phase, which is a body-centered cubic. And then when it goes below that, We still have the ferrite, but we'll form something else, a carbide, or sometimes called cementite phase, which is very hard. And we have a peculiar microstructure that's formed at this lower temperature. It's called pearlite, and that's a lamellar structure of the ferrite and carbide that's formed from the phase, the gamma phase, that has the eutectoid composition. And so that will determine this amount of pearlite. As we move further over here, we're going to form more pearlite. We're over here in this range, and this chemistry will form only ferrite, and the material will be softer if we do that. So these become important to us in terms of this is where we hot roll the steel. This is where we're going to be in the shop when we're working with it. And what the metallurgist can do is he can use these phase changes to change actually the strength of the steel. So if we look at what happens at this temperature level, what's going to happen is we have the austenite here, and as it's going through that change in temperature, as it's going below that eutectoid temperature, we're going to start forming the carbide. And so we have a migration of the carbon atoms from the austenite into the carbide and forming the alpha phase, the ferrite phase of the remainder. And we get a lamellar structure, this layered structure of ferrite and carbide, and it's that structure that we call pearlite. So pearlite is a microstructure, not a phase, but it's very important. And a metallurgist would call our steels, they'd call them ferrite pearlite steels. And that would be the way they would describe them. Now, what's important to us is that what we're going to see is that we can go from here quickly down to here and form some other phases. And we'll talk about that in terms of heat treatment and how we can heat treat the steel to get higher strength by not following down along this curve slowly. This phase diagram is an equilibrium phase diagram. So these phases occur if you hold it at that temperature. And if we cool it in the normal thing, we can get other things. So this provides methods of increasing the strength of the steel. We can do that by adding alloy content, which is expensive and sometimes reduces the weldability. I just want to mention also the cheapest way to do it is increase carbon, but that leads to problems that we'll see later on in terms of welding. So we don't do it that way. The other way to do it is to quench and temper the steel. And so we can do that with lower alloy requirements. And for example, that's how we make the A325 and A490 bolts. It's also how we make HPS 70W and HPS 100W steels. And there's an alternate way, a more modern way also of producing moderate strength steels, which was with TMCP processing, which means that we're going to play around with the temperatures and the rolling as the steel cools down and do this inline processing. So if we look at the time it takes for the transformation from austenite into pearlite, we can look at it in terms of a cooling curve. And so this is temperature shown here, and this is time in seconds this way. And these lines here represent how long it takes at a given temperature to start the austenite to pearlite transformation. And if you get to this line, then that transformation is complete. So you show two different cooling curves here. If you follow this curve coming down, you'll never transform the austenite into pearlite. And if you cool down below this line, you'll form a different microstructure called Martensite. And Martensite's an unstable microstructure. And it's called unstable because it doesn't exist on that equilibrium phase diagram. And Martensite's a hard and brittle material. If we cool it down, and it comes down over on this side of the line, then we'll transform to pearlite. So we have two options. If we want to just end up with our ferrite pearlite steel, we'll want to go on this side of the curve. If we want to form the Martensite, we want to cool it quickly, and so we want to be on this side, a rapid cooling rate. And what's important is where these lines are that represent the start and end of the transformation. Higher alloys, higher carbon steels tend to move this to the right, and which makes the steel easier to harden, which we'll see later on also means it makes it hard to weld. So what a steel manufacturer can do is he can heat treat the steel and perform this quench and tempering. After he's rolled the plate, he'll reheat it in a furnace. So this shows a plate going into the furnace. And he'll heat it up into the austenizing range and then quench it. And he'll quench it quickly, usually with water quench. It's typically done in a roller quenching where the plate is going through a series of water jets coming off the roller like this. And so it's a continuous process. And after that's done, we have a Martensite structure, which is not really what we want because it's very hard and brittle. So to get it back to more usable steel, what we'll do is we'll temper it. So you heat it up in the 800 to 1200 degrees and hold it at that temperature and then cool it down. And that will give us tempered Martensite. The higher the tempering temperature, go up to the highest temperature, the softer the tempered Martensite will be. So the lower the tempering temperature, the less softening we will get. So that's how the mill and the producer controls the strength of the material. Then the next step is just to let it cool, and we have the finished plate. So that's called quenched and tempered steel, and that's used on some of the grade 70 and some of the grade 100 steels that we use in bridges and also in buildings. Now there's another way to do this, okay, and that's called with TMCP. And I'm just showing you, these are two sort of regimes. The conventional process would we start up here at a high temperature, and these wiggly lines are to show where we're doing the roll forming, or we're rolling the plate. So if you did this, the conventional way would be to do that up in this area in the austenizing range, and then it would cool down, and we'd have the as-rolled plate. You can modify that process. You can still do the rolling up at that temperature, cool it down, and then take it back up and normalize it. And this is done to improve the properties of the plate and make them more uniform. And then there's an intermediate step, which is done where you do the rolling at a high temperature, but then as it cools down into this range, you do some additional controlled rolling. And this is to give you a little bit more strength at this temperature. But if you want to take this further, you go to the TMCP process, where we'll do some of the rolling up here, some down at this temperature, and some down at a lower temperature. And the manufacturer has to measure the temperature in the rolling mill and then work out how much reduction he's going to do at each one. You can also do it like this with normal rolling, take it back down, reheat it, and do some more processing afterwards. He can do it like this, depending on what temperature he wants to work with. You can do lower the rolling temperature down here and do it down in this range. And then you can do something else that's sort of interesting, is you'll do some rolling up here, some rolling here, and then cool it quickly down in this range. And this is not to form Martensite, it was just to accelerate the cooling to give him a better grain structure. And this is done in some of the jumbo shapes. If you know about the issues in terms of the properties at the K region of a jumbo shape, this is how some producers improve those properties. They cool that area locally to get better properties out of it. So let's look at this relative to the welding. It's very important to understand that the reason we have chemistry controls on the plate material is so that we can weld it. We need to control that chemistry to provide a steel that's weldable. And that's, if you want to look at, let's say, the relative difference between like the specifications for reinforcing steel versus structural steel. What you'll see is much more chemistry control on the structural steels, and that's to provide the weldability and the other properties that we want. So if we look at welding, and just to briefly look at what goes on, this is showing submerged arc welding, and what you have to think about is welding is fusion welding. So what's going on when we make a weld is we're going to melt the electrode and we're going to melt the base metal. So we'll have a liquid pool of metal, which will go through that same cooling behavior that we just talked about for the structural steel. But we don't want to form martensite during this welding process. So what we need to do is have a steel that doesn't harden easily, and we need to control that cooling rate. And part of the way to do that is to do with some preheating. And this shows just a preheating torch at the front of the welding process where we're preheating the flange, in this case to eliminate any moisture, but also to increase its temperature so it cools slower. And that means if it cools slower, we won't have likely form martensite. So if you look now at a weld in that phase diagram, so what we've got here is this is just half of a weld here, and this part here is the part that was a liquid, okay? So that's the weld metal. And that chemistry of the weld metal is a function of the base metal and the chemistry of the electrode. And that's why it's important also to control the chemistry of the base metal. But also what's critical is this area right here, the heat affected zone, because it starts out here at in the austenitic range. And so if it cools too quickly and cools down here very quickly, what will form is martensite. So what we want to do is we want to control the hardening of this area right next to the weld. As we move further away, what's going to happen is we'll get areas that are not heated to such a high temperature, and so we'll have slightly different structures of the material. And we call this area the heat affected zone. So it's abbreviated as HAZ. And that means that that's area in the plate that's been heated up and its structure has changed because it's been heated, but it hasn't been melted. So this represents the line, the fusion line of everything that's been melted. This material has not been melted, but it's been heated up into these higher temperatures. And so we have to watch out for the structure of that material and make sure it has the desired properties. It just shows a close-up of a two-pass weld to show you the heat affected zone. The first weld pass is right here. The second weld pass was put on here. And what you see is this shaded area. This is the fusion line right here. This is the heat affected zone. And what's really critical is this region right here, the coarser region. You'll also see there's a heat affected zone in the weld pass that we welded on top of. And this actually can improve the toughness of the weld. But we're interested in this behavior. So this is shown schematically over here. Again, this is the fusion line, and this is the coarse grain heat affected zone that we're worried about. And so this is the area that we want to control the cooling rate. And just as an aside, this is the reason why, for instance, welding a very high alloy steel, like you might say a 4340 or something that you might use for bolting, why it's not going to work well for welding, because what happens is it's a very easy material to harden, and what you'll end up is a very hard heat affected zone and possible cracking in that area. So what we want to do is control the cooling rates. Now, if we're making quenched and tempered steel, we add alloys to improve the hardenability. And the reason why we want to do that is we want to move the curve to the right so that the center of the plate, which cools the slowest, will still transform the martensite. We need fast cooling. We want to quench it to form martensite, which is hard and brittle, and then we're going to temper it to reheat. And by reheating it, and it'll form this tougher tempered martensite. On the other hand, when we're welding, what we want is slow cooling to prevent the formation of martensite. So how do we do that? Well, will preheat to slow the cooling rate. That is, we'll heat up the plate to a higher temperature, and that'll slow the cooling rate of the weld. The cooling of the weld is by conduction of the heat into the plate, not by convection of the air going over it. So the bigger the plate, the thicker the plate, the bigger the heat sink, the faster the cooling rate. So the thicker the plate, we need to preheat more. Alloyed steel and high carbon steel requires slower cooling rate because that curve moves to the right, and so those plates will also need higher preheat. So when we look at the welding that has to be done, you'll see that we go to higher strength steels, higher carbon steels, we have to go to higher preheats. Now let's look at just what we have in terms of the bridge steels. All right, we sort of covered the metallurgy of it, and this is what the plate looks like when it comes in. This part over here is parts where it's been trimmed off because we square up the plate from the rolled edges. And the specifications that we've had for bridge steels are sort of summarized here. The first ones in the 50s, they go back further than this, but this is the last 60 years. We started with A7, and then we developed A36, which is what we still have to today. It started in the 60s. Then there was A514 introduced, which was 100 KSI T1 type steels. Then we had the microalloyed A572 grade 50 steel, and then the weathering steels, which were the A588. Today, what we have done is we've combined all of these steels into one specification, ASTM 709. So it includes all of these steels plus the newer steels, the HPS, puts them all into one place where all the special requirements for bridge steels are contained. So when you're ordering steel for a bridge, you order it through the A709 specification. And if you do that, then you'll get all the extra things that are required for bridge steels. So if you look at what's in A709, there's actually 7 grades. So if you're looking for like what was A36, that would be grade 36. And if you're looking for something that was like A572, that's grade 50. And then the weathering steels are 50W. So when it has a W after it, that means it's a weathering steel. And then we have what are called the high performance steels. You have a grade 50, a 70, and 100. And the maximum thickness of these plates are 4 inches. Only one producer really can go to 4 inches. Most of the mills are limited to 3 inches. So holding your plate thickness at 3 inches is probably a good idea. The rolled sections, which would be covered under A992, are labeled as grade 50S in the 709 specification. So why the 709? Why a separate one? Well, there's some unique requirements for bridge steels. There's Sharpie V-notch testing requirements, which are typically not applied to building steels. Special requirements for material and fracture critical members, which we'll discuss. There's also special sampling requirements, additional sampling that's done above and beyond what is normally done. And there's limitations on weld repair of the plate, particularly if it's going into a fracture critical one. And all of these are contained within this specification, so it means that you don't have to write out all of these things as special requirements. So let's just review, just to make sure we're all on the same page of what W stands for. That's weathering steel. This is a weathering steel bridge. You can see that it's not painted, and it's actually it's a very attractive solution for areas away from the coastline. What it forms is it's an alloyed steel, which provides a stable rust-like patina. So this steel has additional alloys to provide this. It requires no painting. It is good to wash off the salt. but it's not for underwater or coastal regions. It really won't perform any better if it's underwater. It costs about 10% more than non-weathering steel, but that's more than offset by the lack of painting. So if you don't have to paint it, the cost is about the same as a painted steel. And so it's really cost effective because it also eliminates any field painting. There's no reason to do any maintenance on this after it's put in service. One of the things that you have to be concerned about, though, is that it is going to produce some corrosion staining, and this shows a drip bar. And the idea of this is the water's coming down here with the orange color on it. It will hit this and drain down and won't hit onto the pier and stain the concrete pier. And it's a simple way to do it, and it's quite effective and simple. Now let's talk about high-performance steel. Okay, these are new steels that have come out within the last 20 years. There's HPS 50W. It really, at this point, has no structural advantage. It has higher toughness, but we're not taking an advantage of in the specification. It has some limits in terms of plate length if it's heat treated. HPS 100W has a limited availability and limited use. It's been used in just one or two bridges. Doesn't have a lot of application. The real gem is HPS 70W. It's available up to 4 inches. Over 2 inches, it's generally quenched and tempered by one producer. Only one producer makes it over 1 inch. But it's a steel of choice for areas where you need high strength. It's easy to weld and generally available. So it's used, HPS 70 is primarily used as a flange material in hybrid sections, okay? And now a hybrid section we'll talk about later on. You'll talk about design of plate girders, but we can do some things in plate girders that you can't do with a rolled section. We can use a lower strength web with a higher strength flange. We don't need the strength in the web for flexure, but we need it in the flange, and so that creates a hybrid section. And this 70W is very useful in terms of hybrid sections at the pier of a continuous girder where we have the highest moment. We'll use HPS 70 flanges. And it's also used in the longer spans in the span region on the bottom flange where we have high tension. Has good strength, excellent toughness, and good weldability. Has very low carbon, okay? Just gives us good weldability. It has enhanced weathering capabilities, and it's either produced as rolled, controlled rolled, with TMCP, and then you can use accelerated cooling, or in thicker plates it'll be quenched and tempered. There's a lot of different ways that this can be produced, and each mill has its own recipe and procedures. To give you some idea of the availability, ArcelorMittal can roll it up to 4 inches, and that'll be a quenched and tempered plate. Up to about 1 3/8, they'll do it with TMCP, and that's available in much longer lengths. And the difference between these two is this is controlled by the heat treating furnace. The length of the heat treating furnace, to heat it up and then to temper it, it limits its length to about 50 feet. Nucor steel produces quenched and tempered, and you can see they have the same limitation on plate length. And SSAB goes to 2 inch. They use TMCP. They go out to 95 feet. So in the thinner ones, we can get longer plate lengths. This is just an advantage if you have very long flange sections. Typically, this is not too much of a problem. You're typically not going to be using very long pieces of this because the moment gradient's fairly high at the pier, and so it doesn't necessitate very long pieces. But this is a very useful material. Now let's talk about the additional requirements that are imposed on bridge steels. If you have a member in tension, you have Sharpie V-notch test requirements that are put into the specifications. It's not required for compression members. So this means also compression flanges and also parts of the web and compression. Reason for doing this is we want to have the ability to tolerate cracks large enough to be found during an in-service inspection. So we're using fracture toughness to provide this flaw tolerance. We have increased sampling and higher energy for steels, which we call that are in fracture critical members, and I'll talk to you a little bit more on what that means. When you buy the steel, you designate it as if it's a tension member with a T, and then there'll be a T1 or a T2 or a T3, and those represent the temperature zones, which I'll show you in just a minute. If it's a fracture critical flange, then you would label it with an F and then the temperature zone. And that means that when you order it that way or when you define it that way, it will come with the properties required for those temperature zones and whether it's fracture critical or not, the toughness requirements. Now what we're trying to do with this toughness is, if this is a crack length here and this is time going this way, if it's a fatigue loading, the crack will extend with time. And if we inspect it, well, there'll be some detectable flaw size. And what we want to make sure is, before it reaches its critical flaw size, we're able to find it. And so the way we do that is by putting in fracture toughness to provide a large A critical so that we're guaranteed at least some remaining life after we inspect it. What we'll see in just a minute, we've actually had in the past some steels that were wind bridges that the critical crack size was too small to detect, and that produces an uninspectable structure and a potential problem. Now there's some things we have to look at in terms of how the flaw tolerance works with the steel. I'm plotting here what is called the fracture toughness here. This is a measure of the flaw tolerance of the steel, how tough it is. And we're plotting temperature. And the first curve here is what you would get in what we'll call a quasi-static loading, which is the kind you might do in a tension test where it may take minutes to the maximum load. And you see it at its temperature here, the toughness starts going up. Now if I do that same steel and I test it at an impact loading, and that would be with an impact where the maximum load occurs in milliseconds, you get a curve like this. So if I'm at a temperature like at this level, if I do it at an impact load, I have this toughness. If I'm doing it slowly, I'm way up here. So I have to understand what loading rate I'm at to determine what temperature I need this toughness at. Now it turns out you can estimate the distance between this curve and this curve by this temperature shift, and this has strange units. This yield strength is in KSI, and the temperature shift is in degrees Fahrenheit. So it's a little bit strange. But if we want to go from an impact load to a bridge loading, and the bridge loading means that time to maximum load is of the order of a second. We're not all the way down here. We're about 75% of the temperature shift. Now this we use to set the test temperatures, and we can convert this toughness into what we call a Sharpie V-notch energy. This is the CVN energy, and if you remember from your undergraduate laboratories, the CVN specimen is a 10 millimeter square specimen, about 20 millimeters long with a notch in the center. And what we measure is the energy it takes to fracture that with temperature. If you take that energy and take the square root of it, multiply about 12.5, you get the toughness in KSI square root inch. This is a way to convert the Sharpie to this. Now we use the Sharpie specimen to check out our steels because it's a reasonably inexpensive test. If we go to a true fracture mechanics specimen, that means we have to pre-crack it, and it's very expensive to do it. So we use this to screen our material. So the way we set the toughness for these bridge steels is you as an engineer will pick your lowest anticipated service temperature. So this is how cold you would expect the structure to be when it was in service, in normal service. You pick that, you pick the required toughness, and then what we do is we shift this last over a year to where we'd be dynamic, and that drops us down to the Sharpie curve, because the Sharpie test is a dynamic test. So this sets the test temperature for the Sharpie. So the Sharpie test temperature will be above the last because of the strain rate differences between the bridge loading rate and the Sharpie test. So if we take an example of, let's say we have a 50 KSI steel and the last is 0 degree F, when should we test? So if we take the equation and calculate the temperature shift going to the intermediate one, we get 105 degrees Fahrenheit. So if the last plus that would be 105 degrees. Typically what we do is that we'll test it at room temperature. So we'll use room temperature as the test temperature. Then we need to figure out what toughness we need, and this is just a simple elastic equation. But we're going to say we're going to tolerate a 1-inch crack completely through the member. So if we do that, and we'll say that yield strength, that means we need a toughness of like this. We convert that into a CVN value, and that says we need about 25 foot-pounds. So this would say that if we were doing this, we'd test 3 specimens, we test them at 70 degrees, and the average toughness must exceed 25 foot-pounds. And that's indeed how we've sort of set up the specification. If we go to the non-fracture critical requirements that are in A709, and again, these are for non-fracture critical tension members. These aren't for compression members. In compression members, you don't need toughness because you're not going to generate a fracture in there. But you can see as we go up, going down the table, we have an increase in toughness because we're going up in strength level. And you can see that the test temperature goes down as we move to the colder zone 3 from the zone 1. So we have these adjusted, and these are written right into the 709 spec, so that if you specify that you want zone 2 and it's HPS 70W, they will know that they need to test for 20 foot-pounds at -10. Now let's go back in time to something that triggered this word called fracture critical. And it dates back to the collapse of the Point Pleasant Bridge, which was sometimes called the Silver Bridge. It went across the Ohio River, Point Pleasant, West Virginia. It was built in 1929 and it collapsed in 1967. It was a total collapse. It was designed as a suspension bridge, a cable suspension bridge, so these were all designed as cables with cable hangers. But they were replaced by a contractor alternate by solid I-bars. So rather than having multiple strand cables, these members were made up of 2 I-bars. And there are also I-bar hangers coming down. So this shows the part of the bridge that collapsed on the approach span. And you can see the I-bars, okay? You can see there are 2 I-bars per chain. They're connected by real pins. There's pins going through here. You can see one over here. They were very efficient. They also formed the top chord of the truss on the approach span, so it's a very efficient design. The time of the failure, the bridge was backed up on one side because there was a problem with a stoplight that was backing things up. It wasn't an exceptionally cold day. It was around 30 degrees, but it resulted in the total collapse of the bridge. And so there was a big investigation to find out why did this happen. This just shows you the I-bars. And they were made from a heat-treated 1060 steel. Now, what this means, the 10 series means it's basically a carbon manganese steel. There's not a lot of other alloy in it. And the 60 at the end means it's a high carbon steel. It's 0.6% carbon. Okay, it's about 3 times the carbon content of a modern structural steel. This is the cheapest way to get this high strength steel, and that's what they did. Has low toughness and relatively high strength. It's a forged eye-bar at the end, and connection looked like this, where you have 2 eye-bars going in each direction. What happened was there was a brittle fracture along one eye-bar right here, which then, once it fractured, the load in this eye-bar was carried by this ligament up here. As we'll see, a ductile fracture occurred here. So we lost this force in this eye-bar. It was transferred to here, which put a torque on this connection, and this eye-bar fell off. And once it did, then the bridge collapsed. The investigation was very thorough, and they had to go down and pull the bars up out of the river. And this is the eye-bar that caused the failure. And what they've done is they put this part back together, this part of the fracture together, to show you how much this side opened up before we got this fracture over here. What happened is this is the brittle fracture where it failed first, and you'll notice there's no evidence of any ductility or thickness reduction. But on the left-hand side, if you look, you'll see this pattern here. That's an indication we've had a lot of plastic deformation because the paint has fallen off. And so we had almost a plastic hinge form. This opened way up, a very ductile failure, and finally this failed, and that's when the bridge went. So the important thing about this is, when you look at this, is to understand that this material on the left-hand side behaves like a tensile specimen. It had good ductility, looks really good. It's not a sterling material. Its tensile properties would be similar to a rebar or something like that, but 10 to 14% elongation, not too bad. This side over here, we have no ductility, and this is the same material on both sides. So the lesson that we learned was, well, what happened on that other side? This was the new thing. And if you look closely at it, it's a very flat fracture. There's no necking or anything that happened. This is a brittle fracture. And this is the area where the origin was of the fracture. And what we'll do is, we're going to, in the next slide, this was taken back to the laboratory and the corrosion removed, and this was looked at. And if you look carefully, this is the corner of the eye bar. So this is the surface. This is where the pin was. And you see these little fan-shaped areas right here. Those were the cracks that formed in the eye bar in its 40 years of service. And they're only about 1/8 of an inch deep. That small crack that formed during that time caused that brittle failure. And so the lesson that we learned from this is that what we need is material that can tolerate larger cracks. There's no way that we could find this crack in an in-service inspection. In fact, there was a sister bridge down the river made of the same steel. They attempted to inspect it, but they were unable to reliably find these small cracks, and so the bridge was taken down. So what we need is a crack-tolerant steel, and that led to the requirements for the Sharpie V-notch. Up until the Point Pleasant Bridge, we didn't have any toughness requirements for the steels. We also learned that 2 eye bars did not provide enough reserve strength, and that members, like when we only have 2 eye bars like this, that we might need higher toughness and closer inspection. And so we labeled those members as fracture critical. And we said, well, the reason why they're important is if they fracture, the bridge could collapse. And so we know distinctly that 2 eye bars are not enough. Now we have a lot of bridges with eye bars out there, and most of them multiple eye bars, and it's not a problem. But when when you label it as fracture critical, that means that you expect that if we lost that section, we could have a collapse. So we put special requirements on those. And so we have higher toughness levels for those fracture critical steels. And these are reflected in these tables. So they're higher energy values than what you saw in the previous table. So when you label it as fracture critical, you have to meet these higher requirements. These are the temperature zones that we use. And the reason why we use zones rather than like somebody's coming in and say, well, it's 11 degrees or something like that. It would be impossible for the producer to stock those different plates. So by cutting the country into 3 zones, it works out pretty good. Historically, we started with just zone 2, but the first bridge meeting we had was in Texas, and the Texas guys said it never got down to minus 30. And so that led to zone 1. And chairman of the bridge committee was from Alaska, and he said it gets a lot colder, so that's how we got zone 3. So we ended up with those. And so most of the country is covered by zone 2, and some along the coast and warmer areas it would be zone 1. And when you get up to the northern part of the United States and Alaska, you may be in zone 3. Now there's some special requirements for sampling. If it's a tension non-fracture critical, you do the sampling for the Sharpie V-notch on a heat-based sampling. That one heat of steel is one ladle of steel, one batch of steel, and that's for grade 50 and grade 36. If you're doing a heat-treated steel, which would be the 70Ws and the 100Ws, on those you have to do plate testing frequency. That is, you actually sample the actual plate because you have to. That plate will have unique characteristics based on its heat treatment. If it's fracture critical, it's P testing for all grades, and you test both ends of the plate. So there's more stringent sampling. The only exception would be is if it's normalized, because normalizing the plate provides very uniform behavior. So what we end up is what we call a total fracture control plan, where our goal is bridge face. We've been talking about the specifications for the steel. There's a whole part over here that has to do with enhanced requirements for fabrication, and then you have field inspection that then results in a safe bridge. So we have some new steels, okay? We have a new steel that's coming into the market. It's A1010. It's an expensive steel. It has some use. We have a highly corrosive area where maybe your water is very close to the bottom flange of the girder. You're in a very hostile coastal area. It has corrosion loss about 5 times less than the grade 50W, but it costs a lot more. So it's not something you would generally specify all over. The tempered Martensite, it's only available up to 2 inches. It's a grade 50 steel that we would use for bridges, has good toughness, has some special fabrication requirements. This shows actually it's going into service, and as you can see, it's not like a normal stainless steel. It's a sort of a tan stainless steel. It's not going to look polished like that because it doesn't have the high alloy content, but it provides excellent durability. So this is a bridge in Oregon. There's been 2 bridges in Oregon done. I think there's a couple being done in Iowa now and 1 in Virginia, and there's being some others being looked at. But it's not something that would be used in general for many bridges. It's only in special applications where you really need the corrosion protection or enhanced corrosion behavior. There's also a new specification for hollow structural sections. If you look at the specification A500, which is the typical specification, it says in there it's not for use on dynamically loaded structure. So ASTM 1085 was developed. It has a Sharpie V-notch requirement, so that's in there. At zone 2 requirements, so this will meet zone 1 and zone 2 requirements. Has a maximum on the carbon equivalent, has a maximum yield strength, and it has improved wall tolerances. If you've designed with A500 on a building site, you know you have to discount the thickness by 10%. They're much closer on this one. It also has a minimum corner radius, so it gets better behavior. Now let's talk a little bit about bolts, because there's been some big changes in the specification for structural bolts. They're, you know, an important part of bridge construction. This is the way we typically do our field connections. And we have a new specification for high-strength bolts, and this is both for buildings and bridges. It's F3125. And so it combines the A325, A490, and the various twist-off bolt specifications, plus their metric equivalents. So now, if you want to order a bolt, if you wanted a 325, you would say an F3125 grade A325 bolt. And that would be what you would order. The A325 and A490 specifications are I think, officially out of ASTM. So this is the way to order it. And there's some improvements in these specifications that are very important, and it's going to provide us even better quality fasteners. One of the significant things from a structural engineering standpoint, there was a drop-off in the strength of A325 above 1 inch. It's been changed now that you have the same tensile strength, 120 KSI, for all diameters. Actually, the manufacturers have been able to meet this for a long time, and they've just now written it in as a requirement. So this will mean that large diameter A325s now become a more efficient structural fastener. There's also in Annex 1 table giving the permitted coatings and overtapping requirements for nuts. In the bridge area, generally what's happening is on painted bridges, galvanized fasteners are being used. This is to help out in terms of corrosion protection. It's very difficult to top coat a structural bolt and get good build on the corners, so most owners are now using galvanizing bolts. And that means that they're typically not using A490 bolts, they're using A325s. And you have to overtap those nuts to account for the thickness increase due to the galvanizing. There is a new coating that's been allowed. It's a zinc aluminum applied coating, not a mechanically galvanized or a hot tip galvanized, but it's a sprayed on type coating. And that's available for both 325 and A490. So this is something that will provide the corrosion protection similar to a galvanized bolt, but also can be applied to an A490. And the special requirement that's required for bridge bolts is this rotational capacity test. And this has been hidden in the AASHTO specs and also in the FHWA specs. Now it's put together all in Appendix 2 of this new specification. And this comes based on some research that was done back a long time ago looking at problems with galvanized fasteners. And the problem was they were being over-tapped and then stripping was occurring, and they weren't applying the lubrication. You have to have lubrication on these galvanized fasteners, because if you don't, you get galling of the threads and you can't tighten them. So all of the bolts in the bridge are required to be installed at 7/10 times their tensile strength of the bolt. Now these are very high tensions that we install these bolts. If you take a 7/8 inch 325, the minimum tension is 39,000 pounds. Okay, that's the minimum tension. What you would go if you were looking at a different industry, what we call snug is what they call tight. We started a fairly high tension, and then we want to get to a very high tension so we can utilize this to develop a friction capacity. Now what happens is the tension you can mobilize in a bolt is a function of a lubrication. So at the top is what you would get in the direct tension, and 2 and 3 are what are fairly well lubricated bolts. You see a reduction in ductility and tension, But that's due to the slight torque that's introduced by tightening it. But if you have clean bolts or weathered bolts, you can see this is a clean bolt. This is a required tension of 39 kips, and it never made it. And it would fail actually probably during installation. So that's why we have in the galvanizing specifications or in the bolt specifications this rotational capacity test. What we want is fasteners that look like this, where they have a nice level plateau. If this is the rotation we're getting from turn of the nut, then it doesn't really make much difference. We'll be up at this level. And I think it's important to understand that if we install these bolts properly, and this is the minimum tension, we should be well above it, at least 15% above the minimum tension in a properly installed fastener. So the rotational capacity test that's in there tests both the nut and bolt as an assembly. And this is important because they're typically they can be made by different people, and if they're going to be coated, they need to be coated separately. We want them to put them together and to determine whether the lubrication is sufficient. And the requirement we have is for ductility is that we can take a 325 bolt and take it to twice the installation turns for A325 and a little bit less for A490 without any failure and no stripping. And the tension must exceed 15% of the 15% higher than the minimum, and there should be no evidence of stripping. So that's the test that they have to go through. So this is just to show you what happens. Again, if we look at tension and turns past 10%, this is as received and this is lubricated. Down here is those same bolts, and we're plotting tension versus torque. And you can see what happens is that this one that's with poor lubrication, we have very high torque but very little tension. And this shows you the weakness of using torque to control. If you went in and checked this with a torque wrench and said 800 foot-pounds, well, let's say I wanted to just get to 40 kips. If you use this to calibrate it, you would say, okay, I need about 800 foot-pounds. If you go into this bolt that's as received, 800 foot-pounds won't give you anywhere near the required tension. And that's one of the difficulties of using calibrated wrench and why we want lubricated bolts. One of the things I want to emphasize, because many times engineers are specifying the inspection, the most important thing in terms of properly installing high-strength bolts in the large connections that we have in bridges is the snugging. The purpose of the snugging is to bring the plates in contact so as you tighten adjacent fasteners, it doesn't loosen the initial, the snug fasteners that you started out with. We want to prevent the crosstalk between the bolts. If you have the gaps between them as you're tightening the bolts down, what will happen is it will loosen the adjacent one. This is the most important thing to do, and it's independent of the tightening method. If you're using direct tension indicators, you must do it the same way. The snugging is exactly the same. And this is the stage when you should check. You want to make sure that they're properly snug. If you're using turn of the nut, what you want to do is match mark them after they're snug, so you can just then go back and get a visual evidence of proper tightening. Checking bolt tension with a torque wrench is unreliable and really unnecessary. A couple of footnotes on bolting. We have a new hole size requirement that's actually going through AASHTO right now. It's also, I think, going through AISC. For 1 inch and greater fasteners, the standard hole is now going to be the diameter of the fastener plus 1/8. For bolts less than 1 inch, it'll be the standard of the diameter of the fastener plus a 1/16. So this is being done because there's been problems with the larger diameter bolts, which are typically hot forged bolts. There's this forging seam, and they're not as round, and they won't clear a normal 16th inch hole. So this was to prevent that problem. It's also about the same oversize that's used in metric bolts. There's some other things to note. Sometimes a hole is misdrilled, or something or maybe you're doing some kind of a retrofit. If you have a hole and you want to correct it, what you want to do is put a bolt in it and fully tension it. That'll give you a Category B fatigue strength, the same as a normal bolted connection. You don't want to, if you avoid welding up the hole or anything like that, just put a bolt in and tighten it up. There's some new electric wrenches out that are very light that can be programmed for turn of the nut, which provide a much more reliable method and are gaining popularity. Now let's just talk about anchor rods and bolts. There's an ASTM specification 1554, and it carries grade 55 or grade 36 to grade 105. And essentially, it goes up to 3 inches for the 105, up to 4 inches for the lower strength. All of these grades can be galvanized. There are supplemental requirements if you need to weld them, and they also have Sharpie V-notch specifications. So these are set up and directly applicable for bridge requirements, and are very good, and they can all be galvanized, so they're very good anchor rods. One to be aware of, where it can lead to problems, and we'll look at that in just a minute, is to be tempted to use the A354 grade BD. This is basically a large diameter A490 bolt. You can get it up to 4 inches, okay? So that your people that want to get high tensile forces, this becomes an attractive thing. Actually has a hardness that's greater than A490. It also has this note in the specification. It says that if you're going to tighten them up to above 50%, you might want to look at the A490 specification. And just put down in it some of my advice is to never galvanize them. They're very stress corrosion sensitive. Now there's work going on to change the specification to reduce this hardness and hopefully improve it. But right now, it is, as it stands, you should be aware. And I'm just going to go through where we had a problem was out on the new San Francisco Bay Bridge, which was on these anchor rods. Where in this area, they were, the ends of those were over the pier, and so they had to be embedded into the pier cap. In order to do that, they had short rods here, and they had what is called a top hat down here, so that the rods started down at the bottom here. They put in the bearings and the rest of the fixtures, the girder, and then pulled this rod up and then installed it. And then it was to be grouted. And the problem occurred is that out there in the field, when they sat out there for a couple of years, water got in. And so this just shows the condition of the water, and you can actually see how wet it was. So these rods were sitting in water, and then they were stressed. And after they were stressed and inspected, they noticed that these nuts came up from the washer. And they were stressed not using turn of the nut, they were stressed using a hydraulic jacking system. So we have here 3 nuts showing a rather unusual situation. These are completely loose. And so they're an indication that we've had a fracture. And on close inspection, there were a lot of broken bolts or rods. And the ones that are colored are ones that were found. And at that point, after doing this, the rests were detention. This just shows you the number of breaks that occurred after tensioning. And it's not precise because they weren't inspecting them on a regular basis. But you can see after 12 days, we had 32 bolts break. So there obviously was a problem. And when you look at the fracture surface, you had this area here, very flat, soft, smooth surface. This is an area where we had stress corrosion cracking, which is the cracking of the material under a static load. And then when it got the cracks got to this size, this was the critical crack size. We got a cleavage fracture across here. So if you looked at the fracture surface in the electron microscope, this is what the cleavage fracture looks like. And if you go over to the smoother area, you see this, and you see these fractures like this along grade boundaries, which is an indication of stress corrosion cracking or hydrogen-assisted stress corrosion cracking. And these were environmentally induced hydrogen embrittlement. Hydrogen forms from the galvanic reaction between the steel and the zinc. Tests show that a threshold exists below which no cracking would occur. So in some cases, we could leave the rods in service, but if we had very high stress and some of the rods had very low resistance, they had to be replaced there. One of the things to remember is high strength / hardness plus high stress plus galvanizing plus water can equal cracking. And so you should be very alert to this situation. Don't be tempted to just select a rod at a very high strength level and assume that it's going to work all right. You should be very careful about galvanizing these. Basically, these types of rods should not be used under sustained high tension. So we're reaching the conclusion. So let's just sort of see what we've talked about. Well, we saw that steel strength is a function of the chemistry and the heat treatment and inline processing, the TMCP. Steels with a high alloy or a high carbon content needed to be cooled slower to prevent formation of martensite in the heat affected zone. We have this problem that they may be easy to harden when they're being produced, but when we weld them, we've got to be careful. We don't want that martensite form. The 709 specifications provide all the special requirements for the bridge steels. This is what you should order through. We have this new bolt spec, A3125, which has a new specification for bolts and contains all the special requirements that, such as the rotational capacity test. We have these CVN requirements for the bridge steels for the members in tension, and then they have different requirements for just tension and fracture critical, and it's up to you as a designer to specify. And that we have these special rotational capacity tests that are required for both black and galvanized bolts in bridges. By this rotational capacity test, then we guarantee the bolts can be installed correctly. We have these new steels, the A1010, enhanced corrosion resistance. Its application, because of its high cost, and special and only limited to 2 inches, it really has applications in shorter span bridges in very hostile environments. The new 1085 spec should be considered if you're in the bridge applications because it's got the CVN requirements, tighter thickness control, quarter radius control also, so it reduces the amount of plastic deformation at the corner. This is new on the market and is not available in all sizes, so you need to check on it if you're going to specify it. So that finishes my presentation, and I guess, Christina, you're going to ask for questions or
yes,
ask me questions?
Yes, we have time for a few questions. Just a reminder, if you have not yet asked your questions, you can still type in your questions at this time. And for our first question, I'm going to take us to slide 19. This is about slides 19 and 20. How are the phases measured during steel manufacturing?
They're not. I mean, you're measuring temperature and using the phase diagram to tell you where you are. In order to develop these, what you have to do, you want to make a phase diagram. You have to cool it to this temperature and then stop everything. And so you have to quench it and find out what you've got at that point. So actually, I mean, it's very difficult to generate the phase diagram. So there are phase diagrams for all kinds of alloys, aluminums, all of those. And it's the phase diagram that the the metallurgist uses to set the processing. So we don't actually measure the amount of each phase or anything like that. Does that make sense?
Thank you. Yes, I think it does. I'm going to take us to slide 31 for a similar question. What is the purpose of rolling the steel multiple times during the TMCP process?
You mean at different temperatures? Like along here?
Yes, I believe the question is why is it done repeatedly?
Yeah, first thing, it is done repeatedly even at one temperature because you can't get the thickness reduction in just one rolling, okay? So it's a progressive reduction. But this is all part of trying to get the desired properties. And don't ask me. This is all secret stuff. But it's all by trial and error, and that I really don't have an answer.
Okay. Thank you. The next question is, are there issues with field welding in cold temperatures?
Oh, yeah. No. In fact, when we get to the fabrication, and we have definite preheat temperatures that the steel has to be at before we weld it. So there will be some minimum temperatures, because if it's too cold, we're going to get a problem with that Martensite. So there are preheat temperatures specified in the welding specification.
Okay, thank you. I'm going to take us to slide 38, where you discussed some of the previous steel material specifications. Why was usage of ASTM A514 stopped in 2009?
Because HPS 100W came along. A514 was not a very good steel for bridges. It was difficult to weld, and it didn't have as good a toughness as the HPS 100W. So it's basically been outdated.
Okay, thank you. The next couple questions have to do with the example at the end of your presentation. The first question is, in the new Bay Bridge, if the A354 grade BD rods were not galvanized, would they not have fractured?
That's likely. That's true.
And could you briefly explain again how the rods failed and how the water got in?
Oh, okay. If we go to slide 86. What happened is that well, let's go back. I think actually you have to go back to 84. I'm sorry. Okay. All right. Can you see my arrow? These are the rods. And what happened is, in order to build this bridge, they actually had to build another bridge to support it. You see the truss here. Because this is not a normal suspension bridge. It's a self-anchored suspension bridge. So you can't hang the deck from the main cables. So they were supporting the bridge as they were building it on another truss underneath and holding it up. And after they got everything in place, then they could lower it down in the piers. And so they had to then, before they lowered it down, this is a bearing. This is a bearing. These are shear keys, and they had to place those in between the bridge deck and the pier cap. So there was no way to stick these rods in from the top. So they had to have them sitting in there. These rods, which they are continuous all the way through, they could just push up through and tighten them than normal. But these couldn't. So they stored these in the pier cap while they were building the bridge. And so if you go now to slide 86, this is the top of the pier cap. These are the rods right here. And they're down below the surface. This is where the shear key is going to come on. It's all roughened so that you get good bond. And so what happened was they're sitting on a horizontal surface out in the bay, and it rains and the water gets in there. They weren't sealed. and they actually what they're doing here is trying to remove some of the water, but there was water trapped in these, and then when they grouted it, they weren't able to eliminate that water.
Okay, great, thank you. So we have a couple of questions on slide 71 regarding the new F3125 specification. Could you confirm that's F3125, not A3125?
Yeah, did I say A? Yeah, it's F.
It's F. Okay, just want to confirm that. And then also, we have a question about specifying what used to be A325 bolts. So now the grade is A325.
That's correct.
And this person would like your recommendation on, does this necessitate a change in how this is referenced in plans and details and notes as well?
Yeah, I would think you have to say F3125 grade A325 would be the proper way.
Okay, thank you.
It's a little bit like specifying A709 grade 50W. Huh? It would be similar.
Okay, great. The next question, for weathering steel connections, moisture between bolted connections has been a problem with bolts popping. Do you know if a solution has been found to prevent this type of failure?
That's interesting. We actually did tests on weathering steel connections and never found that to be a problem if you properly tightened them. There's two things that have been found with weathering steel. There was some early research done that showed if you had large edge distances that you could get pack rust behind them. So there's a limitation in AASHTO on the edge distances and also the center-to-center spacing of the holes to prevent that. And what we found in the research that we did, where we actually weathered connections and we actually just every day would go out and water them, that we had no problem with pack rust or any bolts popping off because the bolts were properly installed. But I think what you'll find is that if you're having that problem, that the plates weren't drawn up and you had gaps. So it either is your plates weren't flat and you weren't able to bring them up at the edge, or the bolts weren't properly installed. Because I think if they're properly installed, that's not a problem. We've got an awful lot of weathering steel bridges out there that haven't shown any of this. But you have to watch the edge distance and you have to install them properly.
Okay, great. And I think we have time for one more question. If part of the web height is in tension and the other part is in compression, does the fracture critical requirement apply to the web portion in tension only?
In terms of the weld, it does. But the plate will be ordered to fracture critical. So the butt weld on the tension side will be subject to the welding requirements and the inspection requirements for fracture critical.
Okay, great. Unfortunately, that's all the time we have tonight for questions. If you did not get your question answered tonight, we will work with Carl to get back to you with an answer by email as soon as possible. And